In this lecture, we're going to be looking at how we actually solve an optimization problem, specifically a linear programming problem, using Microsoft Excel. So the problem we'll look at will be this problem here, where we are maximizing this revenue function subject to these three less than or equal to inequality constraints and all of the variables being non-negative. And recall, in this particular case, we vectorized the problem where we define the matrix A. We see those coefficients come from the left-hand side of these inequality constraints, 9, 10, and 11. And B, the vector, comes from the right-hand side of those three inequality constraints, 20, 100, and 75. In that case, our constraints become this vectorized version AX less than or equal to B, and the vector X greater than or equal to the 0 vector. So we want to set this up in Excel. And the first thing we have to do is go up to Tools and choose the solver. Now, if this is the first time you're using this, you probably don't have the solver actually installed, so you have to go to Excel add-ins, and then you'll see this as an option. So it should be unchecked if you haven't used it before. You check it, you click OK, and then when you go up to Tools, now the solver will appear. And so if we bring up the solver, which we're not quite ready to use yet, this is something that we can sync up all of the data in our problem to actually be solved via the Simplex method. And so we will set up our spreadsheet first with all of our parameters, and then we will look at how you actually sync it up to this solver. So first, let's set up our variables. And so in this case, this is just a label. We have x1, x2, x3, and x4. And let's just say we start off with an initial value of 0 for all of those. We then want to think about our coefficient vector. So when we vectorize this problem, we had this coefficient vector C, which came from the cost. So our coefficient vector C consisted of the numbers 6, 4, 7, 5. And so we can enter those here, 6, 4, 7, 5. And our objective is the dot product of this coefficient vector and our decision variables x1 through x4. And we can set that up with a function in Excel called sum product. So sum product will take the dot product of two different arrays. So in our case, we're going to take the dot product of these decision variables, comma, and these coefficients. And we see we get 0, but just to check, suppose we change our coefficients to 1s. In that case, the dot product should just be the sum of these entries in C. 6 and 4 is 10, plus 7 is 17, plus 5 is 22. So we do see that this is our objective. So this represents the objective in this particular example, the revenue that we want to maximize. Now that we have that set, we want to set up our constraints. So we have constraints, in this case, that we encoded in a matrix A. So we can set up our matrix A. We'll set it up here. And recall, go back over to our problem. Our matrix A, 1, 2, 1, 2, 6, 5, 3, 2, and 3, 4, 9, 12. Okay, so now this gives us our matrix A. And we know we will want each of these, when multiplied by x, to be less than or equal to our entries from B. So let's just label things kind of carefully. We can, what's called, merge these cells so they're together. And we can do the same thing here. And this is just for aesthetics. And maybe center that. So this here represents our matrix A. And what we want is A times X. So remember, the first entry of AX is the dot product of the first row of A and the vector X. So we can again use that sum product function. So we say dot product of this array and this array. Now the way Excel will work is we can drag this formula down, but if we do drag it down, it won't quite work. Let's see what happens. You see Excel will have advanced the formulas for A, which we want, but it also advanced it for X, but we wanted that to be fixed. So the way that you do that is we go up here and we say, okay, it's the cells B2 to E2 that we want fixed. So if we put a $sign in front of the B and the 2, and a $sign in front of the E and the 2, those now will be held fixed when we drag down. And if you look, you can see, say, look at this formula, you can see now we have the 2 correct vectors for the dot product. And the same thing here. We have the 2 correct vectors. So now this here gives us what we want for the left-hand side of each of our constraints. For the right-hand side, we want the entries from our vector B. Recall, those were 20, 100, and 75. Now we also have the constraints that our x's are all greater than or equal to 0, but you'll see that the solver is set up to be able to handle that in a very straightforward way. So we have everything for our problem now encoded here in our Excel spreadsheet. And let's go ahead and bring up the solver. So Tools, Solver. So the first thing, set objective. Well, we know our objective function is what we have highlighted in yellow here, the dot product of our x vector and our coefficient c. And we can choose to maximize or minimize. In our case, we want to maximize. By changing variable cells, those are the cells for our decision variables. In our case, these cells here. Now when we get to the constraints, you can see here, make unconstrained variables non-negative. That, being checked, takes care of our x1, x2, x3, and x4 being non-negative. What remains are these constraints, ax less than or equal to b. And we add them one at a time. So we click Add. And we have, I've tried to set this up so it syncs up nicely with the solver. So cell reference, the first one. This cell, G6, less than or equal to this cell, I6. And notice you could choose equal to, greater than or equal to, or there are these other discrete options which we won't use. But we click OK, and our first constraint is now in. We do the second one. So G7 less than or equal to I7. Add that. Then we can go G8 less than or equal to I8. Okay? And now our solver has our objective, all of our constraints, and our non-negativity constraints on the xi. And so this means we have everything we need. And you can see you can use different solving methods. What we want is simplex. So that's the simplex method for linear programs. And this is kind of a neat interface because we can go into options and you can show iteration results. And what that means is you can see each step of the simplex method if you want. If you turn that off, when we actually solve, when we click solve, it will go right to the optimal feasible solution. But if we do click this, we will see the simplex method in action, and we will see how the method moves from one feasible corner point solution to another feasible corner point solution until it actually gets to an optimal feasible solution. And the key thing to look at now is, remember, these cells here represent our decision variables. So those will change as we iterate through the simplex method. So here we go. Solve. Okay. But this is our optimal feasible solution. So we have x1 is 15, x2 is 0, x3 is 3 1/3, and x4 is 0. And when you look at the constraints, you see that the second and the third constraint are at their bounds, and the first constraint is not at its bound. So in this case, we're producing 15 units of the first product, 0 units of the second product, 3 1/3 units of the third product, and 0 units of the fourth product. But this is how you can use Microsoft Excel's solver to implement the simplex method when you want to actually solve these things. And this is incredibly handy because you can check and see numerically what the solution is. When you're doing linear programming problems in a linear programming class, oftentimes you're doing these things with tableaus by hand, and it can be very handy to use this to check yourself, especially if you turn on the option to show the iterations, because you can see what happens at each step. So this is a very useful tool for us working with linear programming problems.